Welcome to this walkthrough of LeetCode problem number 839, Similar String Groups. In this problem, we'll explore how to group strings based on their similarity and determine the total number of distinct groups. Stick around as we break down the problem and analyze the solution step by step. In this problem, you are given an array of strings called strs, where all the strings have the same length. The goal is to analyze relationships between these strings based on a concept called similarity. Two strings are considered similar if they meet two specific conditions. First, they must have the same length, and second, one string can be transformed into the other by swapping at most two characters, meaning you can change the order of two letters in one string to match the other. For example, the string tars is similar to rats because swapping the first and last characters of tars results in rats. Similarly, rats can be transformed into arts by swapping the first and second characters. Using this definition of similarity, the task is to determine how many groups of similar strings exist in the input array. Within each group, every string is similar to at least one other string in the group. The input to this problem is an array of strings, strs, where all the strings consist only of lowercase English letters. Additionally, the length of the array, strs, can range from 1 to 300, and each string in the array will have a length between 1 and 300 characters. The output is a single integer that represents the number of groups of similar strings in the array. To help clarify the problem, let's look at some examples. In the first example, the input array is tars, rats, arts, star. The output for this example is 2, because the strings form two groups. In the first group, we have tars, rats, arts. Here, tars is similar to rats by swapping t and r, and rats is similar to arts by swapping r and a. Additionally, tars is similar to arts by swapping t and a, so all three strings are connected as part of one group. The second group is star, which does not have any other similar strings, so it forms its own group. In another example, the input is alm. Here, the output is 1 because there is only one group. The strings amv and am are similar to each other because swapping m and v and amv results in am. Since all strings are connected, they form a single group. In the third example, the input is abc, ca, cab, ba, acb, cba. The output here is also 1, because all the strings are permutations of one another, meaning they are all similar. For instance, abc is similar to ca by swapping a and b, and ca is similar to cab by swapping b and c. Similarly, all other pairs of strings are connected through similarity, forming a single group. Some important constraints to consider are that the input array will always have at least one string, and each string will have the same length and consist only of lowercase English letters. Edge cases include scenarios like when the array has only one string, where the output is 1 since there is only one group. If all strings are identical, the output is also 1 because they naturally form a single group. On the other hand, if no string is similar to any other string, each string forms its own group, resulting in an output equal to the length of the array. Lastly, if all strings are permutations of each other, the output is 1 since they are all interconnected through similarity. To solve the problem of determining the number of similar string groups in the given array, we first need to understand what makes two strings similar. Two strings are considered similar if either no changes are needed to make them identical or if swapping exactly two characters can make them the same. One straightforward approach is the brute force method. Here, we compare each string with every other string to check if they meet the similarity condition. To accomplish this, we can define a helper function, is_similar, that takes two strings and checks if they differ in at most two positions. Using this function, we can employ a union-find data structure to group similar strings together. The brute force method is simple to grasp but computationally expensive since we have to compare all pairs of strings, leading to a time complexity of n²*m, where n is the number of strings and m is the length of each string. Additionally, the union-find data structure requires n space to track the membership of each string in its respective group. While the brute force method is conceptually simple, it has significant drawbacks. Comparing all string pairs becomes prohibitively slow as the input size grows. To address this, we can consider a graph-based approach. In this approach, we treat each string as a node in a graph and add an edge between two nodes if their respective strings are similar. The problem then reduces to finding the number of connected components in the graph. To implement this, we first construct the graph by iterating through all pairs of strings and connecting nodes that meet the similarity condition. Once the graph is built, we can use depth-first search, DFS, or breadth-first search, BFS, to traverse and count the connected components. This method is more structured and provides a clear visualization of the connections between strings. However, storing the graph requires significant memory, especially for large inputs, as the adjacency list or matrix can take up n squared space, making it less feasible for scalability. A more efficient strategy involves using union find, or disjoint set union, to dynamically manage the grouping of strings into connected components without explicitly constructing the graph. The intuition is simple: each string initially forms its own group or component, and as we find pairs of similar strings, we merge their groups using the union operation. To implement this, we define the same helper function, is_similar, to check the similarity condition between two strings. Then, for every pair of strings, if they are similar, we use union find to merge their respective groups. Once all pairs are processed, the number of unique components in the union find structure corresponds to the number of similar string groups. The union find approach is efficient, with a time complexity of n squared *m, for comparing all pairs and nearly constant time for the union and find operations. It also uses only n space for the parent and rank arrays, avoiding the memory overhead of storing a graph. However, understanding and implementing union find may be challenging for those unfamiliar with the data structure. After evaluating the different approaches, the union find method emerges as the optimal strategy for solving this problem. It strikes the ideal balance between computational efficiency and memory usage, making it well-suited for handling large inputs. Unlike the brute force method, which is too slow for large datasets, or the graph-based method, which consumes excessive memory for adjacency storage, union find avoids these pitfalls by dynamically managing groups without explicitly constructing a graph. The key realization here is that the problem fundamentally boils down to finding connected components, and union find is the most efficient tool for this task. With a time complexity of n squared *m and space complexity of n, the union find approach scales well and avoids unnecessary computational overhead, making it the clear choice for solving this problem. In this problem, we are tasked with determining how many distinct groups of similar strings exist in a given list of strings. Now, two strings are considered similar if they can be transformed into each other by swapping exactly two characters, or by doing nothing at all. Our goal is to calculate the number of connected groups of such similar strings. To solve this, we will use the union find algorithm, which is also known as disjoint set union. The solution can be broken down into key steps. First, we define the similarity function to determine if two strings are similar. For this, the strings must be of the same length, and they can only differ at exactly two positions, where swapping those characters would make them identical. Additionally, if two strings are already identical, they are also considered similar. Next, we initialize the union find data structure. This includes creating a parent array, where each string starts as its own parent, and a rank array to help optimize the union operation. Each string begins with a rank of 1. This setup will allow us to efficiently track and group connected components as we process the strings. Now that the union find structure is initialized, we proceed to iterate through all pairs of strings in the input list using a nested loop. For each pair, we check if the two strings are similar using the similarity function. If they are, we perform a union operation to group them together. The union operation works by finding the roots of the two strings using the find function. The find function traverses the parent pointers until it reaches the root of the set containing the string. If the roots of the two strings are different, we merge their sets by attaching the smaller tree under the larger tree to maintain balance. This is where the rank array comes into play, as it helps decide the structure of the union to keep the tree balanced. Finally, to determine the number of distinct groups of similar strings, we count the number of unique roots in the parent array after processing all pairs. Each unique root represents a separate group. Using union find here is particularly effective because it allows us to efficiently track and merge connected components, which is exactly what this problem requires. The union find algorithm is especially efficient for problems like this one, thanks to the nearly constant time complexity of its find and union operations, which are alpha, n, where alpha is the inverse Ackermann function. To further optimize the solution, we can reduce the number of pairwise similarity checks by pre-computing and filtering potential pairs based on properties like string length or other common features. This helps avoid unnecessary computations. It's also important to account for edge cases. For instance, strings that are already identical should naturally form their own group. Similarly, strings that differ at more than 2 positions cannot be grouped together because they are not similar. For cases where there is only one string in the input, it will always form its own group since there's nothing else to compare it to. The main data structures we rely on are the union find or disjoint set union structure, the parent array to track the root of each set, and the rank array to manage the balance of the tree during union operations. When analyzing the time complexity of this solution, the similarity check for 2 strings takes O, L, where L is the length of the strings. Since we compare all pairs of strings, the pairwise comparisons contribute an O, n squared, factor, where n is the number of strings. Combining this with the similarity check, the overall complexity becomes O, n squared asterisk L. However, the union and find operations are nearly constant time, O, alpha, n, so they do not dominate the complexity. For space complexity, the union find structure requires storage for the parent and rank arrays, which is O, n. Overall, the space complexity of the solution is linear, O, n. To summarize these ideas, consider the pseudocode implementation. The r_similar function determines whether 2 strings differ at exactly 2 positions or are identical. The find function in the union find structure uses path compression to optimize repeated lookups of the root of a set. This ensures that the algorithm remains efficient even as the number of strings increases. The union function is designed to merge 2 sets by attaching one root to another, based on their rank. If one set has a higher rank, its root becomes the parent of the other set's root. If the ranks are equal, we arbitrarily choose one root and increment its rank. With these helper functions in place, the main number_similar_ groups function begins by initializing the parent and rank arrays for all strings. Then, it iterates through all pairs of strings. For each pair, if the r_similar function returns true, a union operation is performed to group them. Finally, the function counts the number of distinct groups by finding the unique roots across all strings. This count represents the number of connected components or groups of similar strings. The implementation ensures efficiency by leveraging union find's optimized structure and by minimizing redundant computations through path compression and rank balancing. Together, these techniques allow us to solve the problem in a computationally efficient and scalable manner. Here, we begin by defining the solution class and the main method number_similar_groups, which will take a list of strings, strs, as input. Within this method, we first define a helper function, r_similar, to determine whether 2 strings, s1 and s2, are similar. The comparison is done by iterating over the characters of both strings in parallel using the zip function. For each pair of characters, if they differ, we increment a counter called diff. If the difference exceeds 2, the function immediately returns false, as the strings cannot be similar. Otherwise, the function returns true if the difference is exactly 2 or 0. This ensures that similarity is defined as either having no differences or being able to swap 2 characters to match. Next, we define another helper function, dfs, which will perform a depth-first search starting from a given node. This function marks the current node as visited and recursively visits all unvisited neighbors that are similar to the current string. The dfs function helps us explore and mark all strings belonging to the same connected component. We then initialize the number of strings, n, and a visited list to keep track of which strings have already been processed. Additionally, we define a variable, groups, to count the number of connected groups. Finally, we iterate through all the strings using a for loop. If a string has not yet been visited, we increment the groups counter, as this marks the beginning of a new connected component. From there, we call the dfs function on the current string index, I, to explore and mark all strings connected to it as part of the same group. This ensures that all strings similar to the current one are accounted for in this connected component. Once the loop finishes iterating through all the strings, we return the groups variable, which contains the total number of similar string groups in the input list. This implementation effectively uses depth-first search along with the similarity check to identify and count all distinct groups. It ensures that we explore all connections efficiently while adhering to the problem's constraints. Here, we begin by defining the number similar groups method, which takes an array of strings called strs as input. The goal of this method is to determine the number of groups of similar strings. First, we initialize the length of the input array as n, a visited Boolean array to track which strings have been processed, and a groups counter set to 0. Next, we iterate through each string in the array using a for loop. If a string has not yet been visited, we increment the groups counter and call the DFS helper method to explore all strings that belong to the same group. Finally, we return the total count of groups. The DFS method is defined to perform a depth-first traversal, marking the current node as visited and recursively exploring all unvisited strings that are similar to the current one. The rSimilar method, which helps determine if two strings are similar, is defined next. The rSimilar method is designed to compare two strings, S1 and S2, and determine if they are similar based on the problem's criteria. It begins by initializing a diff counter to 0. Then, it iterates through each character of the strings, comparing their corresponding positions. If the characters differ, the diff counter is increment. If at any point the diff exceeds 2, the method immediately returns false, as the strings cannot be similar. At the end of the loop, the method returns true if the diff is exactly 2 or 0, meaning the strings are either identical or can be made identical by swapping two characters. This logic ensures that the similarity condition is efficiently checked for each pair of strings, which is fundamental for grouping them correctly. We begin with an example where the input list of strings is tars, rats, arts, star. First, we initialize some variables. The number of strings, n, is 4. We create a visited array initialized to false, 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 indicating that none of the strings have been processed yet. We also set groups to 0, as we haven't identified any groups so far. Now, we start the outer loop with I equals 0. Since visited, 0, is false, it means the string at index 0, tars, has not been visited yet. This marks the start of a new group, so we increment groups to 1. Next, we perform a depth-first search, or DFS, starting from node equals 0, which corresponds to tars. In the DFS for node equals 0, we first mark visited, 0, as true to indicate that tars has been processed. Then, we compare tars with each of the other strings in the list. When compared with rats, the r_similar function returns true because exactly two positions differ, t and r and t. Since they are similar, we perform a DFS on node equals 1, which corresponds to rats. Next, we compare tars with arts. Again, r_similar returns true because two positions differ, t and at nt. This triggers another DFS, this time on node equals 2, which corresponds to arts. Finally, when comparing tars with star, r_similar returns false because three positions differ. With no further similar strings to explore for tars, we move on to the DFS for the next node, rats. Now in the DFS for node equals 1, which is rats, we mark visited, 1, as true. Comparing rats with arts, the r_similar function returns true, so we perform a DFS on node equals 2. However, since arts has already been visited, we don't process it further. Comparing rats with star, r_similar returns false, so no further action is needed. Moving to the DFS for node equals 2, which is arts, we mark visited, 2, as true. At this point, there are no more unvisited strings similar to arts, so the DFS concludes. Resuming the outer loop, we check I equals 1 and I equals 2, but both indices are already visited. When we reach I equals 3, which corresponds to star, we find that it hasn't been visited, so we start a new group. This increments groups to 2, and we perform a DFS on node equals 3. In this DFS, star is marked as visited, but no further unvisited strings are similar to it. With all nodes processed, the output for this example is groups equals 2. Now let's look at another example with the strings ABC, BAC, cab. First, we initialize the variables. The number of strings, n, is 3, and the visited array is false, false, false. The groups counter is set to 0. In the outer loop, starting with I equals 0, we find that visited, 0, is false, indicating that ABC has not been visited. This marks the beginning of a new group, so we increment groups to 1. We then perform a DFS starting from node equals 0, which corresponds to ABC. In this DFS, we mark visited 0 as true. Comparing ABC with BAC, the r_similar function returns true because exactly two positions differ, so we perform a DFS on node equals 1, which is BAC. Similarly, when comparing ABC with CAB, r_similar also returns true, so another DFS is triggered for node equals 2, which corresponds to CAB. In the DFS for node equals 1, which is BAC, we begin by marking visited 1 as true. After processing, we find no further unvisited strings similar to BAC. Moving to the DFS for node equals 2, which is CAB, we mark visited 2 as true. Again, there are no additional unvisited strings similar to CAB. With all nodes explored, the DFS concludes, and we return to the outer loop. Since all indices have been visited, no new groups are formed. The final output for this example is groups equals 1, as all the strings belong to a single group. Next, we analyze a more complex example with the strings ABCD, ABC, YACT, BACT. As before, we initialize n equals 4, visited equals false, 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 and groups equals 0. Starting the outer loop with I equals 0, we find that visited 0 is false, indicating that ABCD has not been visited. This begins a new group, so we increment groups to 1. Performing a DFS on node equals 0, which is ABCD, we first mark visited 0 as true. Comparing ABCD with ABC, the r_similar function returns true, as two positions differ. This triggers a DFS on node equals 1, which corresponds to ABC. Comparing ABCD with ACT, however, yields false because four positions differ, so no DFS is performed. Similarly, comparing ABCD with BACT also yields false, as three positions differ. In the DFS for node equals 1, which corresponds to ABC, we mark visited 1 as true. After processing, there are no further unvisited strings similar to ABC. Returning to the outer loop, we find that I equals 2 and I equals 3 correspond to strings that haven't been visited. Each of these strings marks the start of a new group, so we increment groups to 3. With all nodes processed, the final output for this example is groups equals 3, as the strings form 3 distinct groups based on similarity. To analyze the time complexity of the solution, let's break it into its primary components. First, the outer loop iterates through all n strings in the STRS list. Each string is processed at most once because the visited array ensures we only process unvisited strings, contributing an O(n) complexity. Next, for each unvisited string, the DFS function is called, which can explore all n strings in the worst case. Within the DFS, there's an inner loop that checks all n strings to find neighbors, so each DFS call performs O(n) work, and across all strings, the DFS traversal contributes O(n)² complexity. Lastly, the r_similar function compares two strings character by character. If each string has a length of m, this comparison takes O(m) time. Since r_similar is invoked O(n)² times, once for every pair of strings, its total cost is O(n)² m. Combining these components, the dominant factor is the O(n)² m cost of similarity checks. When we combine all the components, the overall time complexity of the solution becomes O(n)² m, where n is the number of strings, and m is the length of each string. Now, let's shift to the space complexity. The visited array is a Boolean array of size n, which requires O(n) space to track whether each string has been processed. Additionally, the recursive depth of the DFS function determines the space used by the call stack. In the worst case, where all strings belong to a single connected component, the recursion depth can reach n, contributing O(n) space. Finally, the r_similar function uses only local variables for string comparisons, which adds O(1) auxiliary space. When we sum these contributions, the overall space complexity is O(n), dominated by the visited array and the recursion stack. Let's now consider the best, average, and worst-case scenarios for this algorithm. In the best case, where all strings are identical, each DFS call can mark all strings as visited in a single traversal. However, even in this scenario, the time complexity remains O(n)² m, due to the pairwise r_similar checks. In the average or worst case, where strings are distributed across multiple groups or all are dissimilar, the algorithm still performs O n squared asterisk m similarity checks because every string pair is examined. The worst case time complexity, therefore, remains O n squared asterisk m. Comparing this to a brute force approach, which would explicitly group strings by examining all possible subsets, the naive method would have an exponential complexity of O(2 to the power of n, making it computationally infeasible for larger inputs. In contrast, our solution optimizes the grouping process by using DFS and pairwise similarity checks, achieving a much more efficient polynomial complexity of O n squared asterisk m. To validate our complexity calculation, we can break it down further. The outer loop iterates O n times as it processes each string in the list exactly once. For each unvisited string, a DFS call explores up to n neighbors, contributing O n squared complexity over all strings. Additionally, each pairwise r_similar check takes O m, and since these checks occur O n squared times, this results in O n squared asterisk m as the dominant term. On the space side, the visited array requires O n space, and the recursion stack in the DFS adds another O n in the worst case. As no other significant data structures are used, the total space complexity is O n. Thus, we can conclude that the final time complexity of the algorithm is O n squared asterisk m, and the space complexity is O n. When working on this problem, there are several common mistakes to watch out for. First, some people assume that strings must be adjacent in the array to be considered similar, but similarity is a global property. This means that each string needs to be compared with all others, regardless of their position. Another pitfall is the inefficient implementation of the similarity check. Using nested loops to compare every character of two strings can lead to a slow O n squared asterisk m solution, where n is the number of strings and m is the average string length. Instead, you should optimize this by counting swaps or stopping early if more than two mismatches are found. Additionally, edge cases are often overlooked. For instance, scenarios like an empty array, single character strings, or arrays where all strings are identical need to be explicitly tested to avoid unexpected failures. Errors can also arise from improper union-find implementations. Features like path compression and rank optimization are crucial for maintaining accurate group counts. Lastly, it's important to avoid confusing similarity with anagrams. Similarity is about specific character swaps rather than just matching character frequencies, so the logic must focus on swaps rather than counts alone. Now, let's talk about some key insights for interviews. This problem primarily tests your understanding of graph traversal concepts, such as DFS, BFS, or union find. It's important to emphasize your knowledge of connected components and how they relate to string similarity. Optimization is another critical focus area. Highlight how you reduce redundant checks by stopping similarity comparisons as soon as a mismatch threshold is exceeded and by leveraging efficient data structures. Be prepared to explain the trade-offs between different approaches. For example, both DFS/BFS and UnionFind are valid methods for solving this problem, but you should discuss scenarios where one might be more suitable than the other. Additionally, when discussing your solution, proactively address edge cases like strings of varying lengths, identical strings, or empty input arrays. This demonstrates thoroughness and attention to detail. You can also draw connections to related problems like LeetCode 547, which involves finding connected components in a graph, or LeetCode 721, which requires grouping similar entities. Problems like LeetCode 213-19 also share a focus on connected components and are great references to showcase your broader understanding of these concepts. Finally, let's consider some alternative approaches and their trade-offs. One common approach is to treat the strings as nodes and similarity as edges, and then use DFS or BFS to count connected components. This method is intuitive and works well for smaller datasets, but it can become slower for large inputs due to repeated string comparisons. Its time complexity is O n squared asterisk m, where n is the number of strings and m is the string length, while the space complexity is O n plus e, where e is the number of edges. Another option is the union find approach, which is typically faster because it optimizes the union and find operations using techniques like path compression and union by rank. This results in a time complexity of O n asterisk m plus n asterisk log n, and a space complexity of O n for the parent and rank arrays. Lastly, you can use an adjacency matrix to pre-compute similarities between strings. This avoids redundant similarity calculations during traversal but comes at the cost of higher space usage, specifically n squared. While this trade-off increases memory requirements, it can save computation time in certain scenarios. Each approach has its strengths and weaknesses, so understanding these trade-offs is key to selecting the right method for the given constraints. Great job on completing this problem. In summary, we tackled the challenge using graph traversal techniques to group similar strings. Key takeaways include the importance of graph-based approaches in tools like DFS and UnionFind. Thanks for watching, and see you in the next problem-solving session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!